In this video, we're going to go over the review sheet for circles quiz number 2. So in question number 1, what we have here is a radius and a tangent to the circle. And we know that when a radius and a tangent to the circle intersect, they form a right angle because they are perpendicular to each other. So what we have here is a right triangle. We also know that all radii of a circle are congruent, so it makes sense that this radius is labeled as r, and this radius over here is also labeled as r. Since we have a right triangle, we can set up the Pythagorean theorem to find the missing side length. So we have 12 squared plus the other leg is r squared, and that's equal to 4 plus r squared, because the whole hypotenuse would be 4 plus r. So here we have 144 plus r squared equals to, be careful here, 4 plus r squared is really 4 plus r times 4 plus r. So we do have to distribute. The 4 in here and the r in here. So let's do it. Let me rewrite the first part. I have 16 plus 4r plus 4r plus r squared. If I combine, that's 16 plus 8r plus r squared. Luckily, if I subtract r squared from both sides, it cancels out. So what I have is 144 is equal to 16 plus 8r. Now all I have to do is subtract 16 from both sides and then divide by 8 to get the r by itself. So 144 minus 16 is 128. So I have 128 is equal to 8r. And then from here, I'm just going to divide by 8. And I got that r is equal to 16. Okay. In number 2, we have lines AE and BD that are tangents to circle O and P. And something to keep in mind is when we have two tangents to a circle that come out of the same point, they're equal to each other. So since AC and BC are both tangent to circle O, and they come out of the same point C, they're going to be equal to each other. And since CD and CE are both tangent to circle P, and they come out of the same point C, they're going to be congruent to each other as well. Now, they also tell us the ratio of some of the segments. The ratio of AC to CE is 5 to 3. So I'm going to represent the 5 part as 5x and the 3 part as 3x. And they also tell us the entire length of segment BD has to equal to 56. Well, if these are equal to each other and these are equal to each other, then the sum of this plus this and this plus this must be equal to each other. The entire length of BD must be equal to the entire length of AE, because if we're combining the same two parts together, we got to get the same sum. So I can make an equation that says the 5x part of the line segment plus the 3x part of the line segment equals to 56. Another way of thinking of that is if this part is 5x, then this part also has to be 5x because these are both congruent to each other. And if this part's 3x, then this part also has to be 3x. So now, if I know that BD is 56, that's the 5x part plus the 3x part making the 56. So that's 8x is equal to 56. And 56 divided by 8 is 7. So 7 is the x value, but what we're looking for is the length of CD. CD is the 3x part, so 3 times 7 is 21. So the length of CD would be 21. Moving along. Here, we have more tangents to the circle. So circles X and Y have two tangents drawn to them from point T. So since TC and TS are both tangent to circle X and come out of the same point, these whole tangent lines should be congruent to each other. And since TA and TE are both tangent to circle Y, and they both come out of the same point T, they should be congruent to each other. They tell us the ratio of TA to AC is 1 to 3. So I'm going to represent TA as X, or 1X, and AC as 3X. And we know that the whole line TS is 24. So that means this whole thing is 24 as well. So we can make an equation that says 3x plus x, the two parts, equal the total of 24. So we have 4x is equal to 24. So x is equal to 6. And they're asking us for SE. Now, this is the x part over here. So that makes this the 3x part since they're going to equal to the same sum. So SE is the 3x part. So 3 times the x value of 6 would be 18 for the length of SE. Okay. In the accompanying diagram, cabins B and G are located on the shore of a circular lake, and cabin L is located near the lake. Point D is a dock on the lakeshore and is collinear with cabins B and L. The road between cabins G and L is 8 miles long, so we're talking about the length of segment GL, and is tangent to the lake. The path between cabin L and dock D is 4 miles long. So that's between L and D. That's the outside part of the secant to the circle. And we're looking for the length of BD. So we're talking about segments formed by tangents and secants. So we're going to use our rule whole times outside equals whole times outside. So the whole tangent is 8, and the outside part of the tangent is also 8. The whole secant is 4 plus x, and the outside part is 4. So here we have 64 is equal to, now to distribute the 4, 16 plus 4x. Now from here, let's subtract 16 from both sides. 64 minus 16 is 48. And then let me divide by 4, and I get x is equal to 12. And x is BD, so we found what we were looking for here. Moving along. In number 5, notice how we have intersecting chords. And in the question, it's telling us the length of segments. AE is x, EB is x plus 1, CE is x minus 1, and ED is 2x. And we need to find the length of AE. So remember, when we have intersecting chords, the part times the part of one chord equals to the part times the part of the other chord. So this would be x times x plus 1 is equal to x minus 1 times 2x. Distribute, and I have x squared plus x is equal to, distribute once again, 2x squared minus 2x. Okay. Subtract x squared from both sides, and I have x is equal to x squared minus 2x. Subtract x from both sides because I do have a quadratic, so I want to make it equal to 0. So I have 0 is equal to x squared minus 3x. I don't have a trinomial, so I can't do what multiplies to the third term and adds up to the second term. But I do notice that there's a GCF in common. The x is in common. So I'm going to factor out the x. And when I factor out the x, there's an x left over because x times x is x squared. And there's a minus 3 left over because x times minus 3 is negative 3x. So we have two solutions. We have x is equal to 0, and we have x minus 3 is equal to 0. If I add 3 to both sides, that's x is equal to 3. Now, it doesn't make sense for our length of AE to be 0. If it was, we wouldn't be able to see it. It wouldn't represent the length of a segment. So our length of AE, which is x, has to be 3. So the length of AE is 3. Okay. Here we have a quadrilateral inscribed in a circle so that its vertex points are completely on the circle. And as you guys learned in your Edpuzzle video a couple of weeks ago, this is called a cyclic quadrilateral. And the only thing you need to know about the cyclic quadrilateral is that its opposite angles are supplementary. Don't confuse that with when we learned about regular quadrilaterals like parallelograms, squares, and rectangles. In regular quadrilaterals like parallelograms, squares, and rectangles, the opposite angles are congruent. But when we're talking about quadrilaterals inside a circle, the opposite angles are supplementary to each other. So that means if this angle here, A, is 110, angle C needs to be 70 degrees because opposite angles are supplementary. And if this is 72, angle B, then the angle opposite from it needs to be 180 minus 72, which is 108. So I found my answer. Angle ADC is 108 degrees. Okay, moving down over here. I noticed the word area. What is the area? So I'm going to be talking about sector area here because we're talking about the area of a section of a circle. Now, in the question, it says that the sprinkler is spraying water in a circular pattern and it rotates through an angle of 300 degrees. 300 degrees is not here. That would be too small. That's not 300 degrees. So we're actually talking about here. So be careful. The shaded part is the sector that we're finding the area of because the shaded sector represents how the sprinkler is spraying water at a 300-degree angle. That's most of a circle. And I know there's degrees right away, so I know that we're going to be working in degrees here and not radians because I see that degree symbol. And we're finding the area of the sector because it does say what is the area. So I'm going to set up my proportion. Part over whole equals to part over whole. And remember, this part is about area. If we were talking about arc length, that would be circumference instead, but we're talking about area. And then we have here the central angles. That's the same as the arc length proportion. So area of the sector of the section of the circle, the shaded part, is what we're actually trying to find here. So that will be x. And area of the whole circle, area of a circle is pi r squared. So area of this whole circle would be pi 15 squared. 15 squared is 225. So that would be 225 pi. The central angle was given to us. The central angle of the shaded region is 300 degrees, and our total of the central angles in the circle is 360 degrees. Cross multiply, we have 360x is equal to 300 times 225, 67500 pi. And then I'm going to divide both sides by 360. And I got that x is approximately 108, well, is equal to, I shouldn't say approximately, 187.5 pi. The question does say to round to the nearest square foot. That means the nearest whole number. So I am going to put the pi into my calculator. So I'm going to multiply by pi. I'm going to push the pi button. And that is approximately 589 square feet. So that would be the answer to this question. Next one, I noticed that it's also talking about area of the shaded sector, but this time it's giving us the area of the sector. So we're going to be solving for something else. And just looking quickly ahead in the question, it says, what is the measure of angle N? So we're going to be solving for the measurement of this angle right here, angle N. So they give us the area of the shaded sector. So I know that this is a sector area question. And they give us that that area is 2 pi centimeters squared. And our answer choices are in degrees. So I know that we're going to be finding the angle in degrees and not radians. So if we're talking about the shaded sector over here, let's go to our proportion. We have part over whole is equal to part over whole, just like before. One part is for area and the other part is for central angles because it is an area of the sector question. Now the shaded sector is given us they give us an area of 2 pi centimeters squared. So that is the area of that part of the circle, of the shaded part. And the area of the whole circle is pi r squared. And they did give us the radius. Well, no, they give us the diameter. The diameter is 6. So the radius would be half of that, which would be 3. So 3 squared is 9. So the area of the whole circle would be 9 pi. Now, this part of the proportion is the central angle of the sector that we're talking about. And we're talking about the shaded sector. But we don't know what the central angle is. So we need to actually find that. And then once we find that, we can probably find the angle that we're looking for at the end. And our answer choices are all in degrees, so I'm going to use 360 degrees. Okay, I'm going to cross multiply this way. So that's 360 times 2, which is 720. And then I'm going to cross multiply the other way. And that's 9 pi times our missing central angle. I just used theta to represent that. To get theta by itself, I'm going to divide both sides by 9 pi. And notice how the pi's cancel out. There's one on the top and the bottom. And I got 80 degrees for the central angle. So I'm going to change this over here to what it actually is. This is 80 degrees. And since this is a central angle, that means the measure of its intercepted arc is also 80 degrees because central angles have an equal measure to their intercepted arcs. And notice how angle N is an inscribed angle that intercepts arc ML. So it's half the measure of the arc, so that would be 40 degrees. So angle N is 40 degrees. Okay, moving on to the next question. So we have that PA is tangent to the circle at point A. We have a diameter. We have angle P is 40 degrees. And the ratio of arc CD to arc DA is 1 to 8. So I'm going to express this as the 1 part, 1x. And I'm going to express DA as the 8 part, so as 8x. And since I know that this is a diameter, I know that together these two arcs need to make 180 degrees. So I'm just going to quickly set up an equation, 8x plus x equals to 180. So that's 9x equals to 180. And if I divide 180 by 9, I get x is equal to 20. So now I can actually replace this with what the angles actually are. So this was x, so that was 20 degrees. And dA is 8 times 20. So that would be 160 degrees. So that makes it a little bit simpler. So now we answered the first part, we found arc AD. So the next part is find arc AB. So notice how arc AB is intercepted by this outside angle. And we have a theorem that says the outside angle is equal to half the difference of the intercepted arcs. So and let me use a different color for this. So angle P, which is the outside angle, which is 40 degrees, is equal to half the difference of its intercepted arcs. So its big intercepted arc would be 160, and its small intercepted arc would be AB, which I'll just call X for now. Multiplying by 2 on both sides, we have 80 is equal to 160 minus X. If I subtract 160, I get negative 80 is equal to negative X. Dividing both sides by negative 1, I have X is equal to 80. So that tells me that AB over here is 80 degrees. That's arc AB. Okay, angle BEA. So angle BEA is this angle right over here. And I notice it's one of two vertical angles. And it's formed by these intersecting chords over here. Now remember, the vertical angles formed by intersecting chords are equal to half the sum of their intercepted arcs. So this angle BEA, we don't know what it is equal to half the sum of its intercepted arcs. One of its intercepted arcs is 20. And the other one, this other vertical angle, is opening up to this 80-degree arc. 80 plus 20 is 100. Half of 100 is 50. So angle BEA is equal to 50 degrees. Okay, moving on to angle BAC. So angle BAC is an inscribed angle, and we know that inscribed angles are half the measure of their intercepted arcs. So first I need to know what its intercepted arc BC is. I know that together these two arcs need to make 180. So if this piece is 80, then that means this piece needs to be 100 degrees, making the inscribed angle 50 degrees because it's half of its intercepted arc. Okay, moving along, the last one is angle PBA, and angle PBA is formed by a tangent to the circle. PB is tangent to the circle because it only intersects the circle at one spot, and a chord in the circle. And notice how its vertex is on the circle. So it's half of the arc that it's opening up to. And the arc that it's opening up to is 80 degrees. So that makes angle PBA 40 degrees. There we go. That used a lot of our angle theorems. It used our outside angle theorem. It used our intersecting chord angle theorem with the vertical angles. And it also used inscribed angles. So that used a lot of stuff that we learned about. Okay, here we need the equation of the line, and this is like the do-nows that we were doing every day for a while. Passing through this point perpendicular to this line. So first we have to take our given line and put it into y equals mx plus b form. So I have y is equal to 6 over 3 is 2, 3 over 3 is 1. So I just divided everything by 3. And now I have the slope. So the perpendicular slope that we're going to be using is the opposite reciprocal of 2 over 1. So that would be negative 1/2. Change the sign and flip the fraction for the reciprocal. Now we need to write the equation of the line that passes through the given point. So I'm going to use point slope form. And into y1, I'm just going to plug the y coordinate of our points. Our perpendicular slope that we're using is negative 1/2. And into x1, I'm going to plug the x coordinate of our point, which is 2. And you can just leave it like this. It is a short answer question. There is no need to solve for y. And over here in our first proof, I am taking a look at the proof statement, and I see that we have to prove a proportion. And we know that proportions come after we prove triangle similar. When we have similar triangles, we have proportional corresponding sides. So first we're going to try to prove the triangle similar, and then after we prove them similar, we can prove the proportion. So BC is I just want to highlight the different segments. So BC is here. CA is here. And we do it in 2 colors. And AB is right here. EC is on the other triangle, so let me use another color. And here's the other side of it. So here are 2 triangles that we're focusing on based on our proof statement. So I'm going to look for angle relationships because I know in 2-column proofs, 99% of the time, the way that we prove things similar is through AA, especially when we don't have numbers. So what did they tell us here? That tangent EC is drawn to diameter AC. That chord BC is parallel to secant ADE. All this stuff is here for a reason. And that chord AB is drawn. So I'm going to draw my statement reason chart. And remember, all of our givens are here for a reason. None of them are there for no reason. So let's go given by given. I'm going to go with our first given first. Tangent EC is drawn to diameter AC. So EC is a tangent to the circle, and AC is a diameter. That means OC is a radius. And that means this is a right angle. Now, the reason for that is a tangent and a radius to a circle form a right angle, are perpendicular. So if we have a diameter, the same thing applies because a diameter is just double a radius, but essentially they are the same thing. One is just double the other. So the same applies when you have a diameter and a radius that meet each other, that intersect. So I'm going to say that over here. I'm going to write here angle C is, and I should be more specific because angle C, somebody could get confused as to what I'm talking about. Angle ACE is a right angle when a tangent to a circle intersects a diameter, they make a right angle. Any way of wording that is absolutely fine. So now that I found a right angle in the blue triangle, I want to try to find a right angle in the purple triangle. And you might be thinking it's this angle, and it is, but we have to explain why. Notice how angle B is an inscribed angle. And I know that because inscribed angles have their vertex on the circle. And notice how it's an inscribed angle that intercepts a semicircle, a half a circle. So since this is 180 degrees, that needs to be 90 because inscribed angles are half the measure of their intercepted arcs. So I'm going to write here, angle B is a right angle. And the short way of putting that reason is an inscribed angle that intercepts a semicircle is a right angle. Once again, that's because a semicircle or half of a circle is 180 degrees. It's 180 degrees, so the inscribed angle is half of that, which is 90. And now that I know that both of these angles are right angles, I can say that they are congruent to each other. And my reason for that is all right angles are congruent to each other. Now my next given is that chord BC is parallel to secant ADE. And from that, I'm going to draw a conclusion. And my conclusion that I'm going to draw is about the alternate interior angles, because we do have parallel lines cut by a transversal. So I'm going to put that over here. Angle BCA is congruent to angle CAD. And I'm going to put my reason. Parallel lines cut by a transversal form congruent alternate interior angles. So from here, that's enough to say that triangle ABC is similar. I'm confusing myself here. Is similar to triangle ACE, and that's by AA. And then after we know the triangles are similar, then we know that the proportion that we're trying to prove involving their corresponding sides is also true. And the reason for that is always the same thing every time you're proving a proportion. Similar triangles have proportional corresponding sides. Next proof, we have circle O. DB is tangent to the circle at B. BC and BA are chords, and C is the midpoint of AB. So C is the midpoint of AB, of arc AB. So that means that C is splitting arc AB into two equal parts. Definitely not drawn to scale. It doesn't even look like C is in the middle of arc AB. And they really should have named it arc ACB. But I know it's talking about this direction because in the other direction, C is not there to split it in half to be the midpoint of it. We need to prove that angle ABC is congruent to angle CBD. Now, what I'm going to do, actually, this proof is really, really simple. This is an inscribed angle, so it's half of its arc. And this is an angle formed by a tangent and a chord, so it's half of this arc. So they have to be the same as each other because their arcs are the same and they're both half of their arcs. So that's pretty simple. Let's write it up. That one really didn't require that much. So gonna not put my givens. So I need to put how I knew these arcs were congruent because that's going to be important. So I'm going to say arc AC is congruent to arc CB, and I knew that from C being the midpoint. So I know that a midpoint splits an arc into two congruent parts. And then I know that angle ABC is an inscribed angle. And the reason for that is an angle with its vertex on the circle is an inscribed angle. So then I know that angle this angle ABC is half of its intercepted arc AC. And the reason for that is inscribed angles are half their intercepted arc. And then I also know that angle CBD is half of arc CB. And the reason I know that is because an angle formed by a tangent and a chord is half its intercepted arc. So since I know that they're both half of their intercepted arcs, and I already proved in step 2 that their intercepted arcs are the same, then there's no choice but for angle ABC to be congruent to angle CBD, because even though these don't look exactly the same, both of these arcs were proved to already be the same. So that is through substitution, because these are both the same, so they're equal to each other, because we already proved that these arcs were the same. And if you're in doubt between transitive property and substitution, go with substitution. Substitution is the more general version of the transitive property. Transitive property is a specific case that only applies when you have two things congruent to the same thing. Since we have four things going on here, ABC, CBD, arc AC, and arc CB, transitive property does not apply. But when in doubt, just go with substitution. Substitution will always work if you're between which one to use. Okay, next one. So the next one that we need to do is we need to prove the theorem if a secant and a tangent are drawn to a circle from an external point, the products of the lengths of the secant segment and its external segment equals the length of the tangent segment squared. So basically we're proving whole times outside equals to whole times outside. That's what we're proving. We're proving why we have that theorem, whole times outside equals whole times outside. So I see here that we're proving a product. And remember, you can also write this as AB times AB instead of AB squared to get a better sense of what's going on. So we're proving a product. So before we can prove a product, we have to prove a proportion. And before we can prove a proportion, we need to prove that the triangles are similar. And the hint that I added in here, this was actually a Regents question and they didn't give a hint, but the hint that I added in here was, since we need to prove triangles similar and we don't see triangles, let's draw in BC and BD to form triangles. Now we have this triangle over here, and we also have this triangle over here. So let's think about how we're going to prove them similar. We're going to be looking for angles again, congruent angles for AA. So let's see what we can come up with. My bad, I didn't look at the proof statement. Let me backtrack here because I don't know what triangles I'm focusing on. So let me use black to draw in the segments. So I'm going to draw in, oops, I wanted to use the line. My bad. The line doesn't want to work now. Here's the line. There we go. Okay, let me use my proof statement to figure out what I'm focusing on. AC, so AC is here. AD is actually from the large triangle. And then AB, there's an AB in this small triangle here. So that's one of our triangles that we're focusing on. But then AB is also part of the big triangle. So from our proof statement, from the segments mentioned in our product, we're actually focusing on the big blue triangle. and on the purple triangle. So first, I'm going to look for a shared angle, since I do see that the small triangle is inside the larger triangle. So that tells me that one of our angles is probably going to be shared. And that would be angle A. Angle A is inside the small purple triangle, and at the same time, it's inside the big blue triangle. So let me start my statement reason chart. And I'm not going to write down all of these givens. Okay, so I'm going to say angle A is congruent to angle A, and that is by the reflexive property. So now I need to find another angle that's the same in the big triangle and in the small triangle. So let's figure this out. Oh, so I see here that this angle, since it's formed by a tangent and a chord, that would be half of its intercepted arc, kind of like an inscribed angle, right? It looks like an inscribed angle. Its vertex is on the circle. So it's half of arc BC. And if I take a look at the big blue triangle, I see this angle is an inscribed angle that also intercepts arc BC. So since these are both half of the same intercepted arc BC, they have to be congruent to each other. And that's our second pair of angles. So let's just write that down. Angle ABC equals to half of arc BC. And let me put my reason why. An angle formed by a tangent and a chord is half its intercepted arc. And let me say also that angle D over here is an inscribed angle. And I know that because an angle with its vertex on the circle is inscribed. Since it's an inscribed angle, I know that angle D is half of its intercepted arc, which is also BC. And I'm going to put the reason why. Inscribed angles are half their intercepted arcs. Now, since angle D and angle ABC are both half of arc BC of the same arc, that means that they have to be congruent to each other. And that's the transitive property. But if you're in doubt, you could just write substitution for that. But we do have two things that are congruent to the same third thing, so that means they have to be congruent to each other. So from here, now I have my two congruent angles. So I can say triangle ABD, the blue triangle, is similar to triangle ABC, the small purple triangle, and that's by AA. So now from here, I can prove a proportion involving the corresponding sides. And I just want to make sure that my proportion cross multiplies to give me the product I'm trying to prove. So I'm going to take the first over here and divide by the last over here. Then I'm going to take the first on this side and divide by the last on the other side. And just to double check it out, when I cross multiply, that's AC times AD equals to AB times AB, or AB squared, as it says in the original proof statement. And let me put my reasons. My proportion is true because similar triangles have proportional corresponding sides. And my product is true because in a proportion, the product of the means equals the product of the extremes. Definitely review your circle constructions. These two are the big ones. Oh, these three. And they're the easier ones, but those are the big ones. Wait. My bad. These two are the big ones. And those are the easier ones, but they're the big ones. These two are in the video, the weekly recap video. They were also in your Edpuzzle video. And they're a little bit more challenging. One of these is going to be the bonus question on your quiz.